forces. Right? Right?
Yes.
It needs you to understand
Your
your forces, right?
Yeah.
So it means that I'll
Yeah, okay.
just go a bit, back a bit, and talk a bit about forces, right? And then from talking about forces, then we enter what? Our work energy and power, right? So let's talk about forces a bit. Right? Let's talk about forces a bit, right? So here what I want to talk about, I'll just talk about how forces are on a flat plane and how forces are on a what? Inclined plane, right? Right? And draw a bit of free body diagrams, right? Right?
Yes.
Okay. So when we're talking about a flat plane like this, right? And you are told that there's an object moving left or right, right? Or maybe the object is going that side, right? The object is going that side. So this is our force applied and we're having frictional force. Apart from these two forces, which other forces do we have? Normal force,
Gravitational
and gravitational
and Jesus
force, right? So if this is the case, normal force and gravitational force, do we put them in our equation when we're solving for the acceleration or when we're trying to find the F net? No, right? We don't include them. Why don't we include them? Because these are what? Perpendicular forces. They are perpendicular to the what? To the plane, right? Perpendicular to the surface, right? So here we only consider force applied and frictional force to find our F net, right?
Yes.
So this is when we're talking about the flat surface. So it means that normal force and gravitational force, they don't what? They don't mention this, right? And then we move to an inclined plane. I always deal with inclined plane situations because these are the most complicated situations when we're dealing with physics, right?
Yes.
When we're dealing with forces. So if we're having an object moving upwards at a force F, right? And we're also having what? Frictional force. Which other force do we have? We have normal force, which is also acting perpendicular to the surface. And we're having what? Gravitational force, which is straight downward. Right? This one we have two components. We're having f jet x and f jet what? Y. Or fg parallel, fg perpendicular. Right? So this is our fg at y. And this is our fg at x. So how do you find our f jet x? Our fg at x is equal to mass gravitational acceleration sin theta, right? To find this fg at x, right?
Yes.
So we are having this situation. So how many forces are acting to the plane? There are three forces, right? We are having force applied, frictional force, and fg at x, right?
Yeah.
So it means that if this is going up the plane, how many forces are going up the plane? It's only one force, which is what? F applied, right? So we're only having one force applied that is going upwards, right? And how many forces are opposing the motion of this object? Two forces, right? So two forces are going in the opposite direction, which is Fg at x and frictional force. So what does it say about this? It says that if an object is moving up the plane, it fights against friction and it also fights against Fg at x, right?
An object is moving on it.
When an object is moving up the incline, it fights against F jet x and frictional force. Two forces, right? But if our object now is moving down a slope, if this is our slope, an object is moving down the slope, right? So don't forget that frictional force is always opposite the motion. So it means that our frictional force here to be going backwards and this is our applied force, right?
Yeah.
And if this is the case, what do we know about F jet x? We know that F jet x is now favoring the motion, right? So which forces are going with the motion? It is force applied and Fg at x. It means that now the object only needs to fight against what? Frictional force. So there's only one opposing force, which is Fg. sorry, which is
FF.
frictional force, right? So this is what I want to explain about forces, right? Because when you get in work, they give a problem, right? And one last thing, what about FZ FG, I mean, are we including it in our calculations? Yes, right? As FZ what? At X, right? Yes, FG we're including here as FZ X, right? But here FG we're not including it, right? But here we're including it as FZ what? At X, right? And FZ always X downwards, right? No matter the situation, it will X downwards. Either the object is going up the plane or down the plane. This always X what? Downwards, right? So let's get to work. Work and energy, right? Work and energy. So let me just remind you of the things that we did in grade 10, right? We did something in grade 10 about work. Do you remember? Or energy? We did the energy principles in grade 10, right? First thing first, what is energy? The ability to do work. Okay? What is energy? So in grade 10, you learned about some other things, right? In grade 10. What did you learn about in grade 10? You learned about mechanical energy, right? Do you remember that?
Yeah.
What is mechanical energy? Mechanical energy is the sum of potential energy and kinetic energy. We learned three types of energy: mechanical energy, kinetic energy, and potential energy. There are three, right? So now let's get into it, right? So in grade 10, we learned the law of conservation of energy, right? Which says that energy cannot be created or destroyed. It can be transferred from one form to another, or transformed from one form to the other, right? Or from one object to the other. That is the law of conservation of energy. And we have the law of conservation of mechanical energy. Law of conservation of mechanical energy. What does it say? The total mechanical energy of an isolated system is what? Conserved. Or it remains constant. Right? The total mechanical energy, right? Energy of an isolated system is conserved or remains constant. Is conserved or remains constant. What does it mean? It means that mechanical energy before any change is equal to the mechanical energy after any change that is happened, right? So this means that our EM initial is equal to our EM final. So mechanical energy will represent by EM, right? EM is mechanical energy. So we said what is EM? It is EK plus EP, right? So this mechanical energy, it is EK initial plus EP initial is equal to EK final plus EP final. But what is EK? EK is half mv squared. So this is our half mv squared initial plus mgh initial is equal to half mv squared final plus mgh final. So where was this working? This formula was working when we were having what? When we are having only gravitational force acting on an object. It means that this system is isolated, as I explained that the total mechanical energy of an isolated system. So it means that there are no any other forces, there's only gravitational force. So this was only working when we're having only gravitational force. There's no frictional force, there's no force applied, there's no what, right? So this, where were we using it in grade 10? We're having situations like this. Where this height, maybe they say this height is 50, right? Yeah. And then maybe this height here is 0 height. So here this is point A and this is point B, right? And they said something, or maybe this object here of 5 kg, right? started at rest. What does at rest mean? Initial velocity was 0. So this thing started at rest here, and then it got to point B, right? And they say, okay, calculate the velocity at point B, right? So how are we doing this? They say there's no frictional force, so it means that it is an isolated system, right? So there's only gravitational force acting on this object, right? So how are we using this to solve? We're using this formula EM is equals to EM final, right? So what will this mean? It will mean that our half mv squared at point A, right? Plus our mgh at point A is equals to our half mv squared at point B plus our mgh at point B, right? So this will be half. What is the mass? 5. And what is our initial velocity? 0, because it is starting at rest. Plus our mgh, our m is 9,8, and what is our height there? 50 meters, right? B equals to half. What is our mass? 5. And our v squared final, we are looking for it, right? At point B, right? Plus what is the mass? 5, 9.8. And what is our height? 0 now, right? Our height at point B is 0, right? Right? So this because this is at the ground level, right? So it means that this whole thing was going to give us 0 because of this 0, right? And this will give us what? 2,450. And this will be 5/2 v squared plus 0, because this also was going to give us 0, right? So here we divide by 5/2. What do we get? 980. And then we put the square root.
1105.
Yeah?
41,8.
31. Right? So it means that our velocity here at point B was that much, right? Is it making sense? So this situation is the situation that we are using in grade 10 about work, right? Because in grade 10 we're avoiding any form of frictional force or force applied. We're only using gravitational force, right? The system was what? Isolated, right? So it means that even if we're having another point here that is maybe 20 meters above the ground, we could have found also the velocity here by using the same situation. It means that here velocity was 0, our height being 50, and here again we're looking for the velocity and our height being what? 20 now, because we're looking at the height of 20. Is it making sense?
Yeah.
Yes. So this is the way that we're using in grade 10. But now we're in grade 12, right? So we need to account for every force, right? So let's see how we can. What's wrong? So now we are in grade 12. Okay? So what do? We deal with work, energy, and power, right? So first thing first, what is work? What is work? That time I asked you what is energy, and you told me it's the ability to do work. Now what is work? So what is work? Yeah, guys.
Electromagnetism.
Of force acting on an object and the displacement, right? That is work. It is the product of force and what? And the displacement, right? So how can we represent that mathematically? We can say work is equal to what? To force multiplied by what?
Changing
by the
X.
displacement, right? So let me give you a trick that Maybe at school they won't give you, right?
Yeah, that one.
So this trick that I'm going to give you is this one. Here at school they'll tell you that you will put cos theta, right? And the theta is representing what? The angle at which the force is acting to the parallel, to the plane, right? 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 So I'll tell you this. No matter if they give you that this object is like this, right? Right? Maybe it's on a flat plane and then it is being acted upon by this force like this, making an angle with the horizontal, right? Because this formula says you must put that angle here, right? So what I'm going to tell you is this. If you are having a situation like this, first thing first, find your f at x, right? So how do you find the f at x of this object? Our f at x is equal to f cos of theta, right? And you find your angle in terms of the parallel component of this, right? 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 Right?
You say in that formula,
Yes.
w equals to f change in x cos theta. We first find fx.
I said if you are given an angle that is not making parallel to the plane, that is not parallel to the plane, that is applied at an angle. Can you see that this is applied at an angle?
Applied at an angle.
Yes. So I said, first thing first, before I can tell you this trick that I want to tell you, this force you must always have it as a straight force, right? And I said, how do you find our f at x? Our f at x is equal to f cos of theta, right? Right? From grade 11 work, f at x is equal to f cos theta, right? So what's the next thing? The next thing is this. We know that you are putting what? Cos theta there, right? So, you know math. And you know science, right? What is the value of cos 0? Cos 0 is equal to 1, right? What is the value of cos 90? 0. What is the value of cos 180? Negative 1. So these are the values that we put here, right? Why do we put them there? We are trying to account for the what? For the direction, right? So if you don't want to use this, or if you think this will confuse you, use your direction. How? You know that if the forces are going there, you can take that direction as your positive. If the object is going there, it means that your direction here, it will be positive. It means that going there to be what? Negative, right? Yeah. So you account for that. It means that if you are trying to apply, to find the work done by any other force, you first know your direction, like where is the object going and where is the force going. If the force is going in the same direction as the what? As the object, then you are putting positive. So it is the same as cos 0. Right?
The same as cos 0.
Yes. If now your object is going there and your force is going there, what does it mean? It means that now your force is a negative force. So you can account this by putting a negative there, or you can just put cos what? 180. Do you get my point?
Oh, when it's positive, when the force is...
When your force is going in the same direction as your object, it is the same as putting cos 0. But at the same time, we know that cos 0 is just what? 1. So it means that it is positive. So you can ignore this and just put your positive force. Do you understand what I said? But now, when the object is going in the opposite direction with your what? With the force in question. So it means that you can either put cos 180 there, or you can just know that your force is going the opposite direction of what? Of the object. So you can just put what? Negative. Because cos 180 is equal to what? Negative 1. So it is the one accounting for the what? For the direction.
So when
yes.
When I put one, when the object is moving in the same direction with force,
yes,
isn't it? It's a positive one. It's equal to 1. So which means I will exclude cos theta.
Yes, you can exclude this cos theta.
I will not use it.
Yes.
I'll just use the f changing x.
Yes. Yes.
When you want, when you're teaching 180, it's about direction.
Yes, it's about direction. So cos 182 just mean your object is going the opposite direction with the motion of the object.
So what about when cos 90, when it's here?
Yes, so I'm going to come to there, right? So Some other forces, they do zero work. Do you remember when I explained like this? I said, when we're having an object here, force applied, frictional force, and you're having normal force and you're having gravitational force, right? I asked, do we include this in our calculations? He said no. And I asked why. It is because they're not acting on the plane, right? So if they're not acting on a plane, they also give us zero weight. They give us zero weight. Because this angle that it is making with where the object is going is what? 90 degrees. And when you put cos 90 is equals to what? Zero. And zero multiplied by any number is what? Zero, right? So did you understand what I just explained now?
Oh, yeah.
Yes, right? So now let's get to business, right? So with work, we have positive work, we have negative work, we have zero work, right? So we have positive work. So what is positive work? Positive work is the work done by a force going in the same direction as motion of the object. It is clear, eh? It is clear, eh? It is when the force is going in the same direction as what? As motion of the object. And you also have, so if you are calculating this, this is going to be work b equals to what? F change in x and then cos of 0. Because it is going in the same direction as motion, right?
Yeah.
And then we are having negative work. So what kind of works are those? It is the work done by a force going in the opposite direction in the opposite direction of motion of the object. Is it making sense? So that is negative work. So this means that so it means that our work will be equals to F change in x cos 180. Right? Because 180 is accounting for what? For the direction. Right? And lastly, we have zero work. Right? Zero work. So what is zero work? It is work done by a force that acts perpendicular to the motion of the object.
Steven,
Yes.
hapo ni ka positive word.
Yes.
Like that cos 0, is it because 0?
Yes.
Is it constant or something?
Like I explained, right? I said this is just to account for the direction. So right now we're talking about things that are going in the same direction as what? Motion. So it means that they're what? They're positive. You can put cos 0 because cos 0 is just 1.
No, like I don't first I sort of like why? Okay, I get it all like that's for the direction.
Yes.
And then cos 0 is the same as 1. But then half of the cos 180 it's going to give us what?
Negative 1.
Negative 1.
Yes. So this negative 1 will just account that this work will be negative. Right? So that's why I said, first thing first, if they give you a force that is acting at a certain angle, first thing first you do what? You put it in f at x. Right? So that this, all this will apply. Right? And what about zero work? Zero work, it means that work is equal to f change in x cos 90, which gives us work being equal to 0. Right? So now let me explain this again. Right? We talked about work, positive work, negative work, and zero work. Right? We talked about this, right? But I explained what is work. What is the law of conservation of energy there in grade 10 work? What did I say? Energy cannot be created or destroyed, it can be transformed from one form to the other, right? So if we're having an object that is here, right? And it is going there, right? And there's a force that is going there. So this is force applied. So this force, is it doing positive work or negative work? Can you please stop writing? Let's check here.
Which force?
Stop writing.
So,
So we said we are making this object. It is moving that direction with this force, right? And I asked, is this force doing positive work or negative work? It is doing positive work, right? So is it adding energy to the object or removing energy from the object? It's adding energy. So all positive works that are done, we are what? We are transferring energy to the the object. What about if it is negative work? Maybe we're having our object there, it is going that direction, and this force is acting there. No, like frictional force. Is it positive work or negative work? Negative work, right? So if it is negative work, what does it mean?
It means that the energy is subtracted.
It is removing energy from the object, right?
Manage the positive, it's cause 0.
No.
It's cause what?
Oh yeah, cause 0.
Thank you very much.
Right? So let's try to see those kind of situations before we move to work net, right? So this first portion is just to explain to us what is positive work, what is negative work, what is zero work, and how everything works around, right? Positive work adds what? Energy. Negative work subtracts energy, right?
Yes.
And zero work does nothing, right? Right? Okay, let's go on. So let's take it to having this object. Right? This object is maybe on an inclined plane, which this object is moving up. This object is 5 kgs.
Yes.
It is moving up with an applied force of 60 newtons, right? And this object, we have Fg, right? And it have frictional force, right? So this frictional force is what? 15 newtons, the frictional force, right? And I ask you, can you please try to find the work done by each of these forces, right? The work done by each of these forces. So first we calculate the work done by force applied, the work done by frictional force, the work done by normal force, and the work done by gravitational force, right? So let's start. So what is the work done by the force applied? So maybe this object moved at a distance of 10 meters, right? So let's start. So work done by force applied will be equals to what? To force applied multiplied by change in x, and then cos of what? 0, right? So this is what is force applied?
15 newtons.
This is 60 newtons, right? Multiplied by the change in, so this is 10, and cos 0, which is 1. So what do we have? 600 joules. It is what? Positive. So this is positive work. So it means that force applied is adding energy to this object, right?
Okay.
Right? So this is the first work done by force applied. Let's go to first work done by the what? Frictional force, right? So work done by frictional force is equal to the force of friction, change in x, cos 180, right? So this is what is the frictional force? 15 newtons multiplied by what? By 10, right? Multiplied by what? Negative 1. So this will give us negative 150 joules, right? What does it mean?
It means it's going to opposite side.
It's negative work. It is removing energy from the object, right? And then lastly, we go to work done by what? Fg. And I said, if you are calculating the work done by Fg, it means that you must calculate the what? Fg at x, right? So what is Fg at x? So Fg at x is equal to mass, gravitational acceleration, and sine of theta, right? Let's say it is making an angle of 30 here, right? So what is the mass? 5, gravitational acceleration, 9.8, and then sine of 30. Which this will give us what? 5 times 9.8, 49, multiplied by sine 30, then 4.5, right?
Same.
10.4.5, right? Yeah. So this is 10.4.5 Newton, right? So this is going in which direction? In the opposite direction of motion, right? So what is the work done by that? So work done by Fg is equals to Fg change in x cos of theta, right? So this is what? This is 24.5 multiplied by what? 10 multiplied by what? Cos 180, because it is moving in the opposite direction, right? So this will be what? 245 joules, right? Negative 245 joules. So what does it mean about this? It is also subtracting from the object, right? So lastly, let's try to calculate the work done by normal force, right? And we know that on an inclined plane, normal force is equal to Fg at what? At 1, right? At an inclined plane. So it means that our normal force is equal to Fg at y, right? What is Fg at y? It is mass gravitational acceleration cos theta, right? So this is 5, 9.8, and then cos of 8. What do we get? What do we get?
24.5.
Huh? 42.44 newtons, right? So what is the work done by the normal force? It is perpendicular to this. So we say work done by normal force is equal to normal force changing x cos of 90, right? So this is 42.44 multiplied by 10 multiplied by 0, which gives us what? 0 joules, right? So this is doing a what? F0 work. We found 3 forces doing what? It's either positive or negative work. One is doing positive work and 2 they're doing what? Negative work. Right? One is doing positive work and the other ones are doing what? Negative work. Right? So apart from just finding the work done by a single force, right? We want to know what is the work done by all forces together. Right? The work done by what? All forces being added together, right? So we found that our work done by the force applied was what? Work by force applied was what? 600. And then work done by frictional force it was what?
150.
Yeah?
Hey,
Work done by
150.
frictional force? Negative 150, guys. Oh. The work done by gravitational force? The work done by gravitational force? Negative 245 joules, right? And the work done by the normal force? 0, right? So now we are having 3 forces that are doing something and 1 force that is just a placeholder, right? So now I said, after finding the work done by each of these forces, we are interested now in finding the what? The work done by all forces together, right? You do what you want. Let's finish this, right? Yeah. So now we are concentrated. We are focusing on what? The work done by what? All of the forces, right? Yeah. What do you think we should do? We should just add the work done by all of the forces, right? Yeah. So this is work net, right? It is what we are going to do now. So there are 2 ways we can find our work net, right? So our work net can be expressed as work done by force 1 plus work done by force 2 plus work done by force 3 and so on, depending on how many forces that you are having, right? So this will be, if we're doing this will be our work net will be equal to 600. This is positive, right? Yeah. Plus our negative 150. Yeah. Plus our negative 245, right? What do you get? 205. It's equal to 205 joules, which is positive. So it means that the net work is a positive work, right? So it means that it is adding energy to the object, right?
So many.
Yes.
Una moment so from here. Would you guys want FGH? Would you want the plans or way tomorrow?
Yes. You find out the way that
Or if you just find the FGH doesn't work like that.
you have to find the way. Yes.
I won't find a book while I was doing example attention. When I was about to finish, with my equals to the put upon
The sigma. So they said, did they write it like that, like work net is equal to? Yeah. So it is equal to the summation, the sum of all the works of all the forces. Right?
That one is not a sigma, it's a sum of sum.
Right? So now I said we can calculate this in two ways, right? Another way that you can calculate this, we can say our work net is equal to F net. Right? Why are we putting F net? Because this is the what? What is F net? It's the sum of all forces acting on a single object. And that object ours was there. It was having force applied, frictional force, and FZ x, right? Or FZ x, what value did you find?
It was
24,5.
So it means that our work net can be, what is our F net? So it is force applied, right? Plus frictional force plus FG at x. Because F net, it is the sum, right, of all the forces acting on what? Single object. And then all these must multiply what? Changing x. If you see, I didn't put cos theta there. Why? Because now this we can account this with the direction that we know, right, of the forces, right? So what do I mean? I mean our object was going up the plane, right? So it means that going up is positive and then going down is negative, right? So how many forces are going up? It's only force applied. How many forces are going down? There are two, FZ and frictional force, right? So it means that our work net here is equal to what is the force applied? 60. Force applied. Plus, and our frictional force? It was 15, right? Right? Plus another force which is FZ which we found negative 24,5. And then all this must multiply what? Changing x. So it means that now our work net is equal to what? If we subtract all this, if we add them together, 60 minus 15 minus 24,5, what do you get?
20,5.
20,5. Yeah? 20,5. So if I find 20,5 and then what is our distance? 10. So it means that our work net is equal to what? 205 joules, which is positive. Can you see that? So we can use either the sum of all works that are being done by different forces, or we can just first find the what? The F net. And F net is equal to what? F1 plus F2 plus F3 and so on. Right?
F6.
Is it making sense?
But this one is
So it means that the work net here, that is being done by this force, it is a positive work, right?
Yeah.
So let me ask you a question, right? If you do a positive work on something, you are giving it energy, right? So if you're giving something energy, what happens? If you go home and eat, you've got energy, right? What do you do with that energy? You do some sort of work, right? You do a lot of things, right? With that energy, right? If you don't eat and then you don't have energy, will you do any work? You won't do any work, right? So it means that adding energy to this object, what are we doing? We are giving it work. We are giving it work, right? When we are giving it energy, we are making it to do something, right?
To work.
So if an object, I push it like this, I gave it work. What happens to this object? It moves, yes. It do what? It moves. So it means that that energy is now being used. It can be used as what? As EK, or it can be used as what?
EP.
EP. Right? Right? So it can be used as what? EK, or it can be used as EP, right?
It is EP is potential.
It's potential energy, right?
Now we have to get anything like
Right? Okay. So now, let's do this now. So we said the object will gain either what? EK or EP, right? So we are moving to something that we call the work energy theorem, right? The work energy theorem, which is the standard formula that we use to calculate anything, right? Depending on that deals with work, right? So we said the what? Work energy theorem, right? How together?
Yeah, we are together.
So if we are having something like this, because right now we're dealing with what? With motion, right? Right? So with the motion of this, what do we know about the motion of objects? We know that Vf squared is equal to V initial squared plus
2 beta x.
change in x, right?
Yeah.
And if we take this side, what do we have?
Which one?
We are having V final squared minus V initial squared equals to 2 acceleration change in x. And if we divide throughout by 2, what are we having?
It's V finally squared over minus V over 2.
It should be what?
That one will cancel. And
Two.
there is over 2.
2, right?
Yeah.
So it will mean that, this will mean that we have half V squared final minus half V squared initial should be equals to acceleration changing x, right? But in Newton's second law, in order to find acceleration, what are we using? We're using F net is equals to mass by acceleration. So it will mean that our acceleration is equals to F net divided by what? By mass, right? So on place of A, we can replace this by that, right? In place of A. So it will mean that our half V squared final minus our half V squared initial is equals to what? F net over M multiplied by change in x. But you don't prefer our formulas with fractions. So let's multiply throughout by what? By M. If we multiply throughout by M, what are we having? This M will multiply this M will multiply this, right? So we end up having half mv squared final minus half mv squared initial is equals to F net changing x, right? What is F net changing x? We dealt with it there.
Huh?
What is this?
Work
It is
net.
So this will be work net. So what is this? Kinetic energy, right?
Yeah.
This is kinetic energy what? Final, right?
Yeah.
So this is EK final minus EK initial is equals to work net, right? But what is this?
Change in EK.
This is change in kinetic energy, right? Final minus initial is the change in something, right? So it will mean that our work net is equals to
Changing EK.
change in EK. This is the standard what? Work energy theorem. It says that the work net is equal to the change in EK. So how can we put that in words? We can put this in words as the work net done on an object, right? By F net, right? Is equal to the object's change in kinetic energy. So what does it mean? Work net, we can also replace this by what? F net changing x. So if you give energy to the object, velocity changes, right? It's either if this work net is negative, it will mean that the object will reduce what? Velocity. And if the work net is positive, it will add energy. Is it making sense? Because just like this object, if I'm pushing it like this, it means that I'm giving it energy, right? So if this energy is more, it means that I'm adding, so it means that velocity will increase from being 0 to being more. And if it is frictional force only acting on this object, it means that it is stopping this object from moving, right? So it means that it is decreasing the what? The velocity of this object. So it means that it will also decrease. Is it making sense? So work net is equal to the change in right? Where?
The wind with weight.
Oh, with weight. I said the work net done on an object by the F net is equal to the object's change in kinetic energy. So it means that if the work net is done on an object, its kinetic energy change.
Or the work done when it's done.
Yes, the kinetic energy of the object will change. Yes. It's either to increase or decrease depending on the type of work that you're having. Right?
Yeah.
If the work net it is positive, it is giving what? The object velocity. I think we agreed that if I push this, if I give it F net, it means that the velocity will change.
Yeah.
It will put that work to that energy to work, right? Because I added energy. So that energy is put to work. So it's either I have positive work or negative work, right? But if I'm giving it positive work, its velocity will change to be more, right? But if I'm giving it negative work, its velocity will change to be less. Is it giving?
Yeah, it's giving.
Right?
Yeah.
So for today, I'll end here on work energy theorem, right? On work energy theorem.
Well, I'm not already going home.
I just say you're going.
No,